right, so yesterday we did like the basics of the atmosphere, and today we're going to go more into climate change. And so this picture shows the signature happening in the Maldives, and so this was like a climate agreement, and the reason they're doing it underwater is because the Maldives are an island country off of the coast of India. They're right here. And so most of the country is actually at or just a couple feet above sea level. And so people don't understand this. When you talk about sea level rise, if I'm on the beach and this silver band right here is the ocean, and sea level comes up a foot, that doesn't mean that sea level comes up a foot and it's a foot more inland. It means that sea level comes up a foot. And that if you're at sea level, if your country is 300,000 square miles and it's all at 1 foot above sea level, then you don't have any land that's above the water. So people don't understand that. Think sea level rise of an inch is just like an inch, but it's an inch this way. And anything right at sea level would be covered in an inch of water. Do you see the difference? I was just make sure you got me on that one. Anyway, the Maldives are beautiful, and these people that live there, it's a small country. They did not bring climate change upon themselves. They're not the main contributors. That would be us, but they're the ones having to pay for it. The costs have been externalized to them. Climate, we talked about this yesterday. It's what the general trend is in your weather over a long period of time. And climate change is not the same thing as global warming. Climate change, when we talk about climate, we talk about temperature, but we also talk about precipitation patterns. So when we talk about climate change, some places on Earth are getting warmer, and that's global warming, but some places are getting a little bit cooler. Some places are getting wetter. Some places are getting more drought. Okay, so we're definitely seeing a change in the patterns of temperature and precipitation. So these are not the same. And I told you guys yesterday, you know, as the Earth becomes warmer, a lot of the storms take that energy and convert it into wind and waves through hurricanes, and so that becomes they become more intense. So global warming, that is part of climate change. There are some places that are getting warmer, but that's only one aspect of it. And so, yes, the Earth's climate has changed and varied naturally throughout time, and I'm going to talk about that today. But the current climatic changes are rapid, and they're due to humans, and the main contributors to climate change are fossil fuel use and deforestation. And so we have to understand how our climate works to be able to understand these phenomena. I saw a news article yesterday, and it said that October 2015, last month, was the hottest October ever recorded. Okay, and then 2014, like I kept the day that this came out on January 17, 2015, and I bought it because it was the front cover of the New York Times. Like 2014 was the hottest year on record ever. And so we're having all this hottest ever, and it's like every month, right? So I'll pass that around. You can look at the front cover. So also, the New York Times, they're doing a special now on Greenland, how the Arctic sea ice in Greenland is just, it's melting, and it's huge rivers of water just flowing into the Atlantic every day. So anyway, factors that influence the climate, obviously the ocean is going to redistribute heat, how much sun it gets. We talked about that yesterday with the differences in the amount of radiation that a place gets and all that. So I got to show you some stuff. I got to draw you some pictures. Not that. Alright, you need to draw this and you need to let it soak in. This is a big deal. Alright, so let's get us a little earth. And let's get us some sunlight coming into the earth. Now, the sun is, I don't know, 93 million miles away. That's the actual number. And there's the sun. Let me ask you a question. Is it hot in space? Is that a thing? Nope. Alright, so here's the thing though. It's warm on the earth though, right? And the sun's light totally goes through space. But space isn't hot and the earth is hot. So would you say it's accurate that we get heat from the sun? Is that an accurate statement? No. So would you like me to explain that to you? That's like a little thought bug, right? So the sun, we ellipses and arches, and I'm just kidding, but that's the thing. What ends up happening when we get light from the sun, the energy that we get from the sun is very short wavelengths, very high energy, mostly visible in ultraviolet radiation. And there's like gamma rays and X-rays and all this, but as far as we're concerned, we have visible light and ultraviolet radiation. And they're very short wavelength, high energy wavelengths. And these can go all the way 93 millimiles through space. And these are coming down, and some of them are getting intercepted by the ozone and the stratosphere. The ultraviolet radiation is getting absorbed there. But what makes it through the atmosphere and through the clouds makes it to the sun, the Earth's surface. Now, in the atmosphere, on the way on through down to the surface of the Earth, we have some gases, greenhouse gases. So let's get us some greenhouse gases. The most abundant and the most important and the most stable greenhouse gas that makes the Earth a nice little toasty place to live in a good way is water vapor. And water vapor is the most abundant greenhouse gas. So these light rays, these waves of ultraviolet and visible light from the sun, they can go straight through that water vapor, no problem, not an issue. Go straight through it, okay? And so let's get some labels going on here. What I have so far, this is UV, invisible light from the sun. And so we have some greenhouse gases. We have water. And, you know, humans are causing greenhouse gas emissions and types to change. So let's get some human-caused ones. Let's get some carbon dioxide, and we'll make that red since it's the one that's really warming the Earth right now. So we have some carbon dioxide, much less abundant than water. Oops. Let me make that a little bit smaller. So we have carbon dioxide, and then, you know, humans are also releasing other greenhouse gases. For example, we have methane, so let's throw in some methane. Methane is actually 20 times, 25 times more powerful as a greenhouse gas than water vapor, so that's important. So we got some methane. Methane is a greenhouse gas. And then I know that we had talked about CFCs, and we had talked about ozone depletion, and the hole in the ozone layer does not cause climate change. Are we okay on that? CFCs cause the depletion. CFCs and HCFCs, the replacement for CFCs after the Montreal Protocol, those are greenhouse gases if they don't go up into the stratosphere. So let that sink in. If they go into the stratosphere, the chlorine can get popped off, go destroying ozone. But if they stay at the ground, they're actually greenhouse gases. So they're really powerful greenhouse gases, like thousands of times more powerful as a greenhouse gas than carbon dioxide.
What do you mean by powerful?
So as far as how much heat they can trap per molecule, and I'm going to get to that. So there's maybe some CFCs or HCFCs, and they're there. You have some things like nitrous oxide, HCFCs, and then we have nitrous oxide. So these smaller human-caused greenhouse gases. Now, this right here, we have this light and ultraviolet radiation coming in from the sun. It can go straight through these greenhouse gases. And these greenhouse gases, tomorrow it's going to be cold outside. And when you go outside in the afternoon, is that not the most magical thing when you go outside and it's cold outside and you get in your car and it's toasty? Is that not nice? So these are kind of like the window in your car or the windows in a greenhouse. These are windows in the atmosphere. They can let light in. It's fine. That's like windows. That's how they work. They let light in, but then they don't let the heat out. So let's get to that. So the ultraviolet radiation, visible light from the sun, it's coming into the atmosphere, going straight through the greenhouse gas is not a problem. Now, here's what you don't understand probably already. The Earth's surface takes that visible light, that ultraviolet radiation, and it absorbs it, and it re-emits it as infrared radiation. Long wave, low energy, infrared radiation. If you have an infrared camera and you take a picture of a person, do you get to see their smiling pretty face? What do you see? You see heat. Infrared radiation is heat. It's part of the electromagnetic spectrum, just like light, right? Infrared radiation is right below red on the visible light spectrum. Like, it's one of the things, you see that in your book, you know, the electromagnetic spectrum, like the rainbow colors and x-rays. You know what I'm talking about? Okay, so infrared radiation is re-emitted from the Earth's surface, and that's what heat is. And then the issue is that these greenhouse gases, that infrared radiation does not just go straight through them. They actually are going to absorb the infrared radiation. Visible light goes straight through, not a problem. The infrared radiation, though, is absorbed and then re-emitted to the ground by the greenhouse gases. So, our Earth is actually not warmed by the sun. I mean, yes, it is. But it's actually warmed by the surface of the Earth. And so when we talk about albedo, when we talk about the poles being covered in white stuff, when we say it reflects light, when it reflects light, not only does it reflect light, it keeps heat from being reflected from the ground, re-emitted from the ground. So there's a little bit more to it than it's just white and it reflects light. No, it doesn't make infrared radiation because it doesn't get absorbed. So there's a little bit more to it. So anyway, the windows in your car will let the light in, but then when you go get in your car tomorrow afternoon, it's going to be nice and toasty because they don't let the heat out. They re-emit the heat toward the surface. Do you see? So that's how the greenhouse effect works. And that's how greenhouses work. They have windows, they let the light in, the surface of the plants and the tables and the ground absorb that light and re-emit it as heat, and it stays warm in the greenhouse. How's it make you feel?
So the hole in the ozone is letting out the heat?
No! This has nothing. Absolutely.
But I was like thinking maybe that like helped.
No. So that's a great question. This is all happening. All of this is happening. All of this is happening in the troposphere. The hole in the ozone layer is way up here. This is not related at all.
Okay.
So, and that's actually on the test. So, like, what layer of the atmosphere is the greenhouse effect occurring in? Totally the troposphere. Weather, climate change, everything. Troposphere. The stratosphere, as far as we're concerned, yes. The whole ozone layer, that's all going down in there. But we good to move on? I slowed down and really took my time on that because that's how important that is. Now the rest of it, not so much. And here's their picture, just the same as mine, right? Totally easy to understand. No. So the light from the sun is coming in, and this does have some good information. The clouds do reflect some light, right? They're white, yeah, that's the thing. And so some of it's reflected by the surface. If the surface is covered in ice, it's going to reflect the light. And then what ends up being absorbed by the surface is re-emitted, and there's my greenhouse gases. They back radiate, which means they send it back down to the ground. And so that's how the surface of the Earth is formed. Now this is really cool. Like, I like the weather, right? We had a super powerful cold front come through last night. And it's not really super cold today. It was chilly this morning, chillier. But you know what happened was last night after the front went through, it was still cloudy. And so those clouds are full of water, which is a greenhouse gas. And so the clouds kept us warm last night. Today, we have high pressure. It is clear as can be. And so tonight, we will have no clouds, and tomorrow will be cold as crap, right? Because we don't have, like, that little blanket. And I will go back and show you something. I should have said this. Did I erase it? The more greenhouse gases we emit into the atmosphere, this is like a blanket, right? Keeps us warm. The thicker this becomes. And that light from the sun comes through it. It doesn't care. That light can go straight through this blanket. But that heat, the infrared radiation, it gets trapped in this. And this just gets thicker and thicker and thicker as we emit more CFCs, carbon dioxide, methane, So, all right, moving on. I'm going to speed up a little bit now. So greenhouse gases, I've just explained all of these things. You should highlight them. I did this. I will point out to you that, water vapor, most abundant, most important greenhouse gas. Ozone is actually a greenhouse gas, like the kind that's down at the ground, the bad one. Yeah. Carbon dioxide, nitrous oxides, and I put that on the slide, methane, and then my CFCs. They're all greenhouse gases. The global warming potential, Calliope was asking me about, like, what do you mean by it being a more powerful greenhouse gas? And so what I mean by that is scientists give different gas molecules numbers that show how powerful they are at absorbing the infrared radiation. And so they're expressed in terms of carbon dioxide as far as their potential. And so methane's number is 25 as far as its global warming potential, because it's 25 times more powerful at absorbing heat. Nitrous oxide is 300 times more powerful, so nitrous oxide is not helping us out. And if we look at this chart on the next slide, you can actually see that the HCFCs, what we use to replace CFCs and our propellants and refrigerants, we use this to replace that. They are 15,000 times more powerful as a greenhouse gas. Oops. So, that's nice. I like hairspray. And I looked at my hairspray. One of the ingredients is hydrofluorocarbon. I mean, and there's something you can do to get around that. Yes, ma'am. Oh, as far as staying in the atmosphere, so carbon dioxide is really long, like centuries. I'd have to look back at the PowerPoint from yesterday. Will you do that for me real quick? Flip back. I mean, just you. Flip back and find the residence time. It was on that graph about halfway through yesterday's PowerPoint. That's a good question. CFCs are pretty long-lived. They're made by scientists, and so they tend to be pretty persistent, but I don't know the time, and it should be on that graph. So remember anthropogenic. When we talk about anthropogenic, we say human caused, right? Y'all find it yet?
It's the same as carbon dioxide.
So it is long. Okay, so that is a problem. Okay, I knew it was a while, but I couldn't quote you at the time. But a lot of those things that humans have created, these persistent organic sort of things, they don't decay, right? So anyway, humans have increased CO2 in parts per million. And we're actually above 400 parts per million now. So if we talk about natural cycles, the natural level that the Earth had stayed at for CO2 was around 275, 280 parts per million, and now we're above 400. And that change has happened in the last 50 years. That's a big increase. And so here this is what I was saying, if we look at methane, nitrous oxide, and carbon dioxide as far as parts per million, we hung out, 2,000 years ago until, the Industrial Revolution, we hung out around 280. And now, the last 50 years, we're, as far as CO2 parts per million, we are about 400 parts per million. So that's, just burning fossil fuels and burning and deforesting trees. So, like I said, the two major causes for rising CO2 are burning fossil fuels and then deforestation. When you remove a tree, you do damage two ways. You've taken up an organism and removed it that can sequester, which means store carbon. And then also, when that tree, if you burn it and when you do combustion, you make CO2. Or if it gets decomposed by decomposers, that makes CO2. So the same byproducts of burning oil are the same byproducts of you burning calories in your body. When you burn calories, you literally are doing like a combustion reaction. You make carbon dioxide and water. And that's what you get if you burn gas, carbon dioxide and water. So, anyway, moving on. Chemistry's fun. Methane levels are the highest they've been in 800,000 years or more. And so where methane comes from, remember methane is CH4. And so do you see any oxygen in that chemical formula?
No.
No, so if you do anaerobic decomposition, that's part of the A, means no or not. Anaerobic decomposition. This aerobic means with oxygen, air, okay, not air. So anaerobic decomposition, if you do that, you don't make CO2. That's kind of impossible because you don't have any O's, okay? You don't have any oxygen. So you're going to make CH4. And so if we look where methane comes from, there's definitely a test question about this. One of these little guys is on there. If we take livestock, cow farts have a lot of methane in them. Let me tell you why. Because if you're decomposing grass or corn or whatever you're feeding them in their guts, they don't have any oxygen in their intestines. It's a low oxygen environment. Landfills, you bury your trash. That's going to be a low oxygen environment because you buried it. And then rice is going to make methane because it's grown in a paddy. And so you have the standing water and you have anaerobic decomposition happening in the pools of water. Because it's standing water, right? Flowing water will get more oxygen, but standing water won't. How you feel? Alright, so that's where those come from. Nitrous oxides, they come from the heat from combustion. We talked about that a lot yesterday. Yes, ma'am?
Is there any other way to grow rice besides like standing water?
I think there's some genetically modified rice that doesn't involve as much water, but that's like saying, can I grow a pecan without a tree? No. I mean, that's just the kind of plant it is, right? But there are some lower water needing kinds, but I mean, as far as needing a paddy, that's a thing. So, anyway, feedlots make nitrous oxides and then fertilizers, right? So we need nitrogen for plants. Remember, nitrogen and phosphorus were the fertilizers we need. This is the same stuff connecting back to agriculture. Ozone levels have increased, and we make ozone in the troposphere. Remember, ozone down at the ground, thumbs down. We make that as a byproduct of smog. We talked about that yesterday. That's a greenhouse gas. CFCs, these are declining because of the Montreal Protocol, but HCFCs are on the rise because we replace them with HCFCs. Water vapor, this thing. Water vapor is the most abundant greenhouse gas. It is the most important greenhouse gas, but we haven't changed the concentrations of it because we're not like making more water. See, we're putting more CO2 into the air because that CO2 was buried 300 million years ago in coal forest. Okay, but the water was never like buried and stored for 300. That didn't happen. But the carbon was stored. It was stored in the fossil fuels that were underneath the Earth's surface. So that's the difference. Aerosols, we talked about these yesterday. Radiated forcing is positive force, that makes it warmer. Negative force cools it. I don't think you'll see this, but there you go. Positive feedback loop. So you need to be familiar with these. We already talked about them. Remember that positive feedback loops are not good. Positive as in growing is where we get the positive feedback loop. That's where we get the name for that. So positive feedback loop, I told y'all yesterday, you know, it's kind of like you get sad and you eat a cookie, and then you're sad that you ate a cookie, so then you eat some more cookies, and then you're sad, and then you just eat the whole box of cookies, and then you get sad, so you eat some more cookies, and then you don't get happy, okay? And so that's a positive feedback loop. A negative feedback loop is, I'm hungry, so I eat a cookie, and now I'm not hungry anymore. It's a sentence. A negative feedback loop doesn't grow. And so when we talk about climate, one of the positive feedback loops that you need to be familiar with, and now I can like make science words go with it because you know more now. But when the Arctic sea ice melts, ice has a high albedo, so it's very reflective, and then we have dark colored water exposed. That water is going to absorb the sunlight and then re-emit infrared radiation, which warms the earth and makes more ice melt. And so then when more ice melts, more dark colored surface is exposed, which decreases the Earth's albedo, so more energy is absorbed and re-emitted as infrared radiation. And so I can just keep saying that sentence all day. That's a positive feedback loop. Negative feedback loop is, now that we have more water evaporating, we have more clouds, and clouds cool the Earth because they reflect light. And that's a sentence, and I'm done. That's a negative feedback loop. See the difference? Okay. So here's the natural cycles. These are called the Milankovitch cycles. That word is on the next slide in your PowerPoint if you want to see what that word looks like. And so I take my little model Earth here. The axial wobble, like here's the axis. If I took a skewer and skewered the Earth right here at the poles, depending on where the pole is pointing. Sometimes the pole points like in different places. You know, it points like in different places. Not that big, like the Earth is not going like that, but it may point this way, it may point that way. So the next is the variation of the tilt. The Earth is tilted 23.5 degrees on its axis, about like this, but it can tilt, it's very subtle, so 24 degrees or like 22 degrees. Yeah, so, and the more tilted it is, the more extreme our seasons are, because you have, like, we're tilted toward the sun in our summer, but then, like, more tilted, right? So, and then the last one is the variation of the orbit. And if you didn't get it when we did with the basketballs, the Earth's seasons are not caused by the fact that sometimes, well, this is called the eccentricity. Have you been in, like, geometry and talk about eccentricity in, like, an oval? Is that a thing? Some of y'all have been like, yes, and some of y'all say that. But, so when you look at, like, a shape, like an ellipse, sometimes it's flatter and sometimes it's more round. This doesn't matter as far as our seasons. That's caused by the tilt of the axis. But like sometimes we are a little bit farther and a little bit closer in parts of this little orbit. But this is not why it causes seasons. And if you look at this cycle, it's about 100,000 year cycle, and we should be getting cooler according to this cycle. So if you want to go natural cycles on me, like, that don't match, okay? So anyway, those are the Milankovitch cycles. They typically go along with periods of glaciation. We are in an ice age right now. Like, believe it or not, that's what we are, like, all the stuff points to ice age. That's not really working out for us, but that's where we should be with the natural cycles. And then the solar output does change. You have sun cycles about every 11 years. That's not on there, but that doesn't, none of those things, none of the things that are natural cycles, none of those are matching up with the climate and how it's changing. What matches up is the CO2 emissions. So anyway, the oceans are our friend. They can actually absorb quite a bit of CO2, which is great for us because that helps to mitigate climate change. But it sucks for anything that lives in the ocean because that whole carbonic acid problem. And I read one of y'all's tests, and y'all talking about CO2, and you were like, and CO2 rains down in the precipitation into the water. No. CO2 is in the atmosphere, and it just dissolves into the water. It just, like, dissolves. There's not, like, a magic slide that it goes down into the water. It's not like an orbit, what's it called? A portal for the CO2. No, it just dissolves in the water. And that makes it acidic. That slows down global warming, so that's great, but it does make the ocean more acidic. Y'all remember when I heated up the soda water and the bubbles came out and it became less acidic? Well, warmer oceans, they're actually not going to be able to hold as much CO2. And so that is slowing down. So if we think about it like that, well, the warmer that we make the Earth, the less CO2 it can hold in the oceans because the oceans are warmer, and so more CO2 is put out into the air, and then the world gets a little warmer, and the CO2 can't be held in the oceans because the oceans are warmer, and so it's a positive feedback loop. So that would help with ocean acidification a little bit, but anyway, oops. So ocean circulation, we had talked about most of this already. I do want to call your attention to El Nino and show you some stuff with this. So on the AP exam, they're not going to be like, hey, when your teacher did that thing with the blow dryer, which way was the blow dryer pointing? And that's probably like where you're understanding. I mean, I know you know a little bit more about it now, but like in your mind, you're probably like, okay, normal. Well, I'm going to draw this out for you. So here's, Southeast Asia, right? And here is South America. And then here's the surface of the Pacific at the equator. And so normal, I'm going to do 3 different colors for you, okay? I'm going to do blue as normal. Here's my trade winds. And then if you go back in your mind, right? We're going to have cold water here, so I'm going to have cool surface water. I'm going to have high pressure, and I'm going to have dry conditions. Do you remember all that? And we're going to have that upwelling, bring nutrients up to the surface. Over here, I'm going to have warm surface water, And then I'm going to have low pressure, and I'm going to have a lot of rain. And I don't have any upwelling. So that's normal. Now, what
Yeah.
what happened?
Do you have download?
Yes. That helps to bring oxygen to the lower parts of the ocean. And that's important, but like on the AP exam, they're going to ask about like the collapse of fisheries over there. But yes, you have like this nice little circle going. Now on the AP exam, what they may ask about fishing, they may ask about drought and fire and stuff, and we're going to get to that. But what they're probably going to ask, and this is on the test tomorrow, is they might ask when you have unusual cooling in the Eastern Pacific, or unusual warming in the Western Pacific, or unusual warming in the Eastern Pacific. Like they're going to ask you about surface temperature of the water. So I made up a little song. Do you want to hear it?
Mm-hmm.
Yeah, okay. So do you know that song where it's like, it's the end of the world as we know it. It's the end. You heard that before? Okay. So what I did is I just made up a little song, and it says, where the wind blows all of the water, it will be warm there. Where the wind blows all of the water, it will be warm there, because it blows all the surface water and piles it up. Do you got a better song? Okay, shut up. No, I'm just kidding. Thank you for the applause, Tyler, because you can actually sing. Feel free to sing it for me later. All right, so let's do some El Nino, okay? So I'm going to do a different color and kind of look at the changes in the surface temperature of the water. So I'm going to make red El Nino. So now the trade winds are going to weaken in reverse. And I'm just going to write in different colors, okay? So where the wind blows all of the water, it will be warm there. See that? And then I have low pressure, and then it's going to rain too much. And so on the AP exam, the unusual warming of the Eastern Pacific is El Nino, and it might flood, right? And I might have landslides or something like that. And then over here, that's warm, so this is cool. So unusual cooling in the Western Pacific is El Nino, and I'm going to have high pressure, and I'm going to have the sunshine and higher atmospheric pressure. They may ask you about pressure changes. That could happen. Probably about the temperature, though. But this little guy, that's going to make for drought and wildfire, and that's what's happening right now in Indonesia, and the chimpanzees and the sad baby chimpanzee. No, with orangutan. Can I act like I didn't say chimpanzee? Orangutan, I'm sorry. Sorry, Indonesia. Thank you, United States. I love that movie. So anyway, let's do La Nina. La Nina is the same as normal. It's just extreme normal. So we're going to throw in like a very warm and a very cool. And so unusual cooling in the Eastern Pacific would be La Nina. So green is La Nina. That's with the very. The red was El Nino. And then the blue is normal. We good? Cool. Yeah. All right, so we got that. Proxy, I think it would be so cool to be a paleoclimatologist. I mean, that would be like Lenny's job. So what they do, paleoclimatologists, they can't like go and unearth like the ancient thermometers that kept temperature readings before humans came along. That was nothing. But they can use proxy indicators. And when I say the word proxy, your ear should hopefully hear the word approximate. See how those are similar? And so proxy indicators are things that we can use to get approximate reads on what the climate used to be like. And so they can shed light on past climate. Ice caps, ice sheets. The thing about ice is they have these trapped air bubbles, and these ice cores, basically they take like a core, like a cylinder, and they pull a core of ice out of the ground, or out of the glacier, really. And so you can look in the bubbles of air, and you can see how much CO2 is in the atmosphere. You can see if there was fires, or you can even look at trapped pollen and see how plants work. You can look at the isotopes of oxygen and actually tell the temperature of the air. I mean, this is a really cool field to go into. Plus, you get to go living in Antarctica some. It's exciting stuff. And ice cores, there are some ice cores they're getting to that are almost 1 million years old, which that's pretty cool. So here's a paleoclimatologist with the ice core, and like I said, the trapped ice bubbles, air bubbles in the ice, they can shed a lot of light on some things. There are other proxies that are not related to ice, so you can actually go back, and then there are some ancient lake beds out west, and you can actually core into those sediments and tell what kind of fossilized pollen are in those sediments. And you can, if it's of a conifer tree that only lives in cold weather, you can tell that it used to be cold there. So that's kind of neat. Tree rings, you can tell from droughts, and we had seen some things with tree rings in our last unit. And then arid areas, you can actually look at these little dens of things. And then coral reefs. Corals, you can also look at the isotopes of like calcium and oxygen, tell the temperature. And there are some types of little plankton that have shells, and depending on the temperature, the shells may curl one way versus another way, and you can like count them and tell the temperature. When I was in college, I took a class on all this, and it was super interesting. But that's a little beyond the scope of this course. But they're like, that's the thing. That's what I want to do when I grow up. I don't want to do this or like be a materials chemist. A materials chemist makes bank, and you just like design new things to put stuff in. I like, or new materials. Like Nike wants a kind of polymer for shoe. Okay, I'm gonna be right on that and make 6 figures. Okay. So anyway, I decided what I want to do when I grow up. This Mauna Loa. Go ahead and highlight all this. What ended up happening with Mauna Loa, that's on the big island of Hawaii, and I actually went there when I went to Hawaii last year. They wouldn't like let me in the lab or anything, but I was like, that's the thing in my textbook that made the climate change research happen. And so got that, right? So let me show you what that looks like. Over the last, I guess it's 50 years now, this readings, the scientist's name was Keeling, like Keeling. Anyway, he had taken all these readings and noticed, starting in 1960, the parts per million for CO2 was around 300. And like I told you now, it's over 400. This is in the last 50 years. And so you can really tell the start of the Industrial Revolution, and then also the start of more people having cars and electricity. And then if you look, you see like this is a year, like each little line is a year. Do you know why that is? The plants, right. And so what Logan is saying, like here's the equator, it cuts right apart above the big part of Brazil, right? You can see it. So if you're ever taking a test, that's where the equator is. But most of the land mass on Earth is in the northern hemisphere. The southern hemisphere, if you look at it, it's like a bunch of ocean. And so in the spring and summer for the northern hemisphere, all the plants are doing photosynthesis and blooming and all that. And they're taking up CO2 and they're doing the photosynthesis. And so the CO2 levels worldwide drop temporarily during our spring and summer. And then when they shed the leaves in the fall and winter and that stuff gets decomposed, it goes up. Isn't that interesting? So each little line, you can tell is a year because of that seasonality that we have. So, and I mean, can't really argue with that data. Pretty good data. Anyway, so climate models, not really going to go into this as much. We talked about the IPCC a little bit with activity on Monday. They're the Intergovernmental Panel on Climate Change. It's composed of hundreds of international scientists and government representatives. And this is the thing, like when I took meteorology and then climate classes in college, like when I went into that class, and this has been like 10, 12 years ago. At that point in my life, climate change was still very controversial. And I was like, totally like, I'm a Republican, climate change ain't a thing, because I was younger and I didn't know, right? Because, here's the thing, after I sat in the class with the lady that got her doctorate in researching ancient tree rings and climate patterns, and like she had been to college for like 12 years, right? And so like that's all she studied was climate. And these people on the IPCC, but they have college degrees in climate, and that's what they like do for a living. So if I'm gonna believe my uncle or my daddy about climate change, or somebody that does this for a living, like let me pick one. Okay, it's not a hard decision, and so like I don't think that the common man that hasn't had a class like this and hadn't been to college and been to classes that you talk to people that study meteorology for a living, they don't get that the wealth of evidence towards this is astounding, and anybody in the scientific community to say that climate change isn't occurring would be like to say the world is flat. I mean, it just reeks of ignorance and lack of scientific education. So, welcome to your science education. But I mean, I'm just, what? Nothing? Okay, so anyway, they release these assessment reports every once in a while, and the Earth's surface temperature on Earth has increased about 1.6 degrees Fahrenheit in the past 100 years. Like I told you, last year was the hottest year on record. Last month was the hottest October ever on record. And we keep having all these records keep getting broken. And here in the southeast United States, we're actually seeing a slightly cooler pattern, especially during our winters. And the last 4 or 5 winters we've had snow, but if you think before that, like, it didn't snow for like years, right? And so this is going to be a pretty snowy winter. So it's kind of interesting, but at the same time, it's kind of alarming. Anyway, so climate change doesn't always mean everywhere's hotter. It means some places are hotter, some places are not. And so if you look at this picture, the places that are seeing the most warming happening, they are in the Arctic. And that picture that I passed around from the New York Times, even though it was made after this picture, they really match. This is a newspaper. Oh, thank you. And so you can see even from this picture, when you look at it, most of the dark red places were up at the North Pole, right? And so where we are is not really warming that much. And there's some places that are cooling. And that's, I mean, like I said, not everywhere is just getting super hot, and you can tell. That's not how it is. But temperatures are increasing, and like I said, we're not really super affected, and on that data from the New York Times, that we weren't really super affected. So anyway, it's getting hotter. Here's the global temperature since 1880. It's getting hotter. I don't know what to tell you. Climate change isn't a thing. There's this quote that I really like, and it says, the thing about science is it's true whether you believe it or not. So you don't have to, people are like, do you believe in this or that? No, I don't believe in it. It's like, are the numbers there? I like science. I like numbers. I like data. I like evidence. That's what I believe in. So anyway, precipitation is changing too. And the unfortunate thing about these precipitation changes is most of the places that are becoming drier are already dry. And so we look at sub-Saharan Africa, they're going to experience more drought. Northern Africa and then this densely populated part of the Mediterranean, basically these places that are either like savanna or chaparral, those biomes are already kind of crispy and dry, that are fueled by fire as far as being able to renew themselves. They're going to become drier. Antarctica is actually becoming wetter. And the reason Antarctica is becoming wetter is because it's becoming warmer. And so with increased temperatures, you have increased evaporation and precipitation. And so the North Pole is also becoming wetter for that same reason. Pretty interesting, right? So anyway, we're not super affected, so we can sit here in our nice happy little bubble and be fine, but everybody ain't fine. So, like I said, there's going to be increased areas of precipitation, increased areas of drought, and then heavy rains are going to contribute to flooding. That's going to kill people, destroy property and houses, millions and billions of dollars of damage happening because of this. You have more snowstorms, more tornadoes, more hurricanes. Everything's just kind of like more extreme than it used to be. Every time there's a hurricane, it's like a record one, right? If it's a snowstorm, it's a record. Everything's a record. But that should be alarming to you. And so there's some blocking patterns. We had already talked about mountaintop glaciers. The thing about mountaintop glaciers, especially in like Indochina, India and China, they're disappearing. And so those glaciers in the Himalayas, and then also glaciers in tropical countries and mountains, those act as water towers, and they store water during the wet season, and then it melts and it provides water for the rivers in the dry season. And so that's good. And then, like, New York Times is doing a series just on Greenland right now and how the melting there is just super fast. That's some really beautiful articles. And like I said, you have more snow in the Arctic because it's warmer, and so you have more evaporation. That's not really helping anybody that lives there because nobody lives there. Here's some pictures of some glaciers melting. We had already talked about this. This is from Glacier National Park, I believe. And then the thing about melting any ice, we've already talked about this a lot, but in case you missed it, there's the positive feedback loop that I referred to. When you melt ice, you expose darker surfaces, and they absorb the light from the sun and re-emit infrared radiation. That makes the Earth warmer. So you should go visit the Maldives and Glacier National Park before those aren't really a thing anymore. It'll just be like National Park for no reason. It'd be great. Permafrost, if you go to the Arctic, that's where it's really getting warmer. Permafrost is this permanently frozen ground, but it's not being permanently frozen anymore. So that's sort of a problem. So these people have established settlements in these places that have been frozen for hundreds of years, and now their towns are just kind of squishing into mud because this frozen ground has a lot of water in it, and it's frozen, so that's fine. But then when it's not frozen, it's a squishy mud mix. Here's another thing about that. Methane is a greenhouse gas, a powerful greenhouse gas, 25 times more powerful than carbon dioxide. And you have all this anaerobic decomposition that happened under that ice because it didn't have any air because it was frozen off from the surface. And so now as this permafrost is melting, all this methane that had been trapped in that permafrost is getting out. And so that's bad positive feedback loop, right? More methane, hotter Earth, more permafrost melting. Positive though, hey, guess what? The sea ice is now exposed, so we can drill for oil easier. In the Arctic Sea, all this is like uncovered and not frozen anymore, so we can totally get up in the North Slope and get all that oil. That's positive feedback loop. So I guess if you want to look for some positives, and we can sell to like Russia easier. Yay! We got that Northern Passage all nailed down now. Oh wait, was it Northwest Passage, right? Is that it, or Northeast Passage? What was the direction of that? Northwest, Northeast? Northeast Passage? Okay, so sorry. Anyway, glaciers melt, they run into the ocean. When we have hurricanes, is that on here? Okay, I'll say that I did. When we have hurricanes, though, it does make the flooding worse. Let me tell you something. I bet you don't know this. Look at these numbers right here. Causes of sea level rise. Whee! So even if none of the sea ice melts or none of the glaciers melt, none of that happens. 57% of the reason why the sea levels are rising is because hot water takes up more space than cold water. Just like hot air in a hot air balloon takes up more space than normal air. So 60% almost of the reason that sea levels are rising is because the water is just warmer. So it doesn't matter if the ice doesn't melt. Like, sea levels are going to come up if the earth gets warmer. This is kind of like when we talked about oil spills in the ocean, how we had said that, about 60% of the oil in the ocean is actually from natural seeps. Like, you don't think about stuff like that. You think about, giant oil spills, or in this case, you think about the glaciers all melting. But it's actually thermal expansion. Who knew that was a thing? I remember the first year I taught this, I was like, what? And I had to look it up, and I was like, what? And so it kind of blew my mind. I don't know if that's blowing your mind right now, but pretty interesting.
Well, I thought ice expands when it gets increased.
But a lot of that's true, but the ice floats above the water, so it don't really matter. See what I mean? And then also a lot of the ice is on land. Like the ice shelf in like Greenland, for example, isn't even in the water. So, but that's a good point. When sea levels rise, what ends up happening with this is like Hurricane Sandy, that was where hurricane, like listen to the sound of my words from now. Like that's when a hurricane hit New York City. That sounds like something off a movie, right? But when sea level is already a little bit higher than it should be, when you get that storm surge, that's really the damaging part of a hurricane. That wave, that temporary rise in sea level, 4 or 5 feet, that's what it is. So 4 or 5 feet, the sea level goes up for a couple days. That makes the storm surge worse. And then most of the places we've destroyed the wetlands that help to soak up the water. So anyway, that was what New York City looked like after Hurricane Sandy. It's just kind of flooded. 53% of people in the United States actually live along the coast. That's kind of scary. And then some places are going to be more prone to getting flooded, these low-lying areas and deltas, like in Bangladesh, and then places like Florida. And then island countries like the Maldives and Tuvalu, they're just right at sea level or a little bit above sea level, so their country is not going to get flooded. I mean, it's just, I mean, it's going to get flooded, but it's going to be gone. So we had already talked about ocean acidification a lot. Global warming is going to modify temperature, and when it does that, it turns out, I don't know if you know this, but it turns out that plants don't have brains. Did you know that's the thing? And so plants are actually regulated by genes that turn on and off based on temperature. Like how else would a plant, like a tree, know to like bloom flowers or make fruit? How else would they know? And so if you like plant a bulb in the ground, like if your mama has like lilies or irises or whatever, but that bulb stays in the ground, and depending on that winter, how cold that winter was, they might come out a little earlier or later. Have you ever noticed that? Well, anyway, when that happens, like if you're a caterpillar that depends on certain types of vegetation, that vegetation might pop out and bloom before you're like hatched. Like maybe those like caterpillar genes aren't exactly regulated by the same thing as plant genes, right? And then also, if you're a bird that's migrating, the vegetation may not match up with your traveling, right? And so these things are the timing of the plants and the timing of the life cycle of the organisms are going to match up. And then also, if you have a certain range of tolerance for temperature, you might have to move toward the poles to find that temperature that you like or that you're adapted to. Or you can move up a mountain. Some mountains, they're already at the top of the mountain. You can't go anywhere. Or you're protected by a park, and that park has borders. And that habitat that you really would like is outside of that protected area. So yeah, you see, this is like a hot mess, right? Hot mess. Y'all need to get on my level. Sorry. I didn't even mean to make that joke, though. I'm so corny. I don't even mean to. Droughts and fires, we had talked about this already. So hunger in developing nations, especially when they don't have that food security. Increased fires, increased heat waves. If you're asking about social effects of climate change, heat waves, expansion of tropical diseases. Let me tell you about that. This is some mess right here. I saw this AP exam question, right? And it was like, how can climate change expand the range of tropical diseases? And this might be one on the test that you're having to do right now. I think it is. I don't know. It has something to do with El Niño too. You can go with it like that. But if we have climate change, it could cause flooding. Do y'all know that mosquitoes, we're going to talk about this in Unit 9, but mosquitoes are vectors for disease. They carry malaria, for example. Well, they do that. They lay their eggs in standing water, like water that's still. And so what ends up happening, if we have flooding, that's going to increase pools of standing water, which will increase the transmission of tropical diseases because they have more places to lay their eggs if we have flooding. If we have drought, running water like rivers, those rivers will start to dry up, and then you'll have increased standing pools of water because it's not flowing anymore, which will increase the transmission of diseases by mosquitoes. Isn't that crazy? Like you can come up with that, but maybe you could, and now you can. So there you go. I turned off my pen. Sorry. So there's that. Let me see if I can get this figured out all by myself. This is not of super huge importance, but it is going to cost a lot of money. And poor nations are going to be at more risk than rich nations because their economies aren't as resilient as ours. They like grow their food and then they eat their food. They don't have like factories and grocery stores and stuff, so it's going to be a problem. Temperature changes. I already said this. Temperature changes are most extreme at the poles. And so I was talking about that whole permafrost thing. I don't think y'all understand what I'm saying when I talk and I say that permafrost, when it melts, it makes the soil a squishy mess and your house falls in. You know, you can't build your house on a squishy surface, like a muddy, unpacked thing. So this is happening all over Alaska. Like, I'm not making this up because I want to like convince you that climate change is real. But this is the thing. If you ever watch, my husband, he only watches like Star Trek and then like the Alaskan wilderness shows, and they have the towns and they'll show the people's houses in the permafrost melting and it'll show their houses squishing in. I'm not making this up. So anyway, here's the Arctic sea ice. By 2070, we won't have but like that little piece. But see, we can get it right here. This is the North Slope of Alaska. That's where everybody's fighting over the oil, and the United States has decided if they actually, President Obama, they started drilling for oil here, and he, I think it was, I don't know if it was Exxon or BP, but he like made them stop. They let them for a minute and then they stopped them because it's just if anything happens and the oil spills up here, the water is so cold, and then when it does freeze, you're not gonna be able to clean it up because it does freeze like seasonally. Like in the winter, it'll freeze and then it'll melt again in the summer. I mean, it's such a sensitive area. There ain't gonna be nothing they can do about it if it does mess up. So anyway, there's your polar bears. And told you about the floating parts, pieces of ice. Those are fewer and far between, and so that's an issue. And so there's that little Eskimo guy trying to go fishing. So there's all the things. All right, so let's see, the climate assessment's kind of released and everything's getting warmer. Yes, we're all going to that. I'm just kidding. But in all seriousness, I mean, this is like a reiteration of all the stuff that I've already said. Are we responsible for it? Probably. There's two things that we can do about climate change. Mitigation, remember mitigation means to lessen. So we can actually start doing things that lessen our greenhouse gas emissions. Probably, you know how the United States is, probably not going to do that. Unless it's mandated by law, and the Senate voted that down 2 days ago. Oops. Adaptation, this is kind of where we are. We're like, you know what? We know the sea is coming in. We'll just build walls to block it out, and then there's going to be a giant hurricane, and we're all going to get flooded. It'll be fine. Leaving the area, let's just pack up and leave. Restricting coastal development. Adjusting the kind of crops that can be grown because of changes in precipitation. So we're probably more on the adaptation side of this. Both are necessary because even if we stop emitting all greenhouse gases today, the residence time for CO2 is centuries. So we're stuck with the problem now. It'd be interesting, like we'll tell our kids, when I was a kid, blah, 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 right? Like, anyway, when we look at CO2 emissions in the United States, electricity is the #1 cause, and the second leading cause of CO2 emissions is transportation. In case you needed to know that, which you will tomorrow. So what can we do to reduce fossil fuel use? We can encourage more efficient use of electricity through better appliances. We can also get more renewable energy. So this could involve wind and solar. Wind, solar, hydrogen. We'll talk about all these next unit. Those are all things that we could do. Got all that? All right. So there are better appliances as far as energy goes. Energy Star appliances use less electricity. You can weatherproof your house, but this is like a contradiction to yesterday's PowerPoint where you like exacerbate your indoor air pollutants if you do. Just open your doors when it's nice outside is the answer. Carbon capture and sequestration, that just means to trap it. We have some ideas for that. But they're still in like research phase. The reason they're still in research phase is because Congress hasn't forced power plants into doing this. So, people don't do things to be nice. It costs a lot of money. And you know, the people that make our electricity, like I like electricity. Do you like electricity? Yeah, me too. So, I mean, and that was going to make it cost more, and that is harder on people in the United States that may not have a lot of money to spare on an extra power bill. So, this is where our money for subsidy should go, into research for this, not into like making oil cheaper. Like that's my opinion of it. Anyway, transportation, like I said, that's the second leading cause, and I didn't mean to give you that answer a second ago, but it's on the test. So, the thing about cars, we could really do a lot to solve our problems with greenhouse gas emissions if we would just get rid of internal combustion engines. We have been using the same model for how we drive cars for 100 years. Like, we went to the moon and we're still using the same kind of engine in our cars. That doesn't make any sense. Only 14% of the energy that you put into your car in gasoline actually makes your car go forward. I bet we could come up with a better way to do this. And if you ever open up your hood and you touch it, that will burn your hand because that combustion engine is hot. Most of that energy is lost as heat. So we got the second law of thermodynamics going crazy right here. This concentrated awesome energy is getting converted to heat, and we can't use that again. And so if you get an electric car, even though you have to burn coal in our area to make electricity, And that makes carbon dioxide when you go, because you don't have to plug your car up, right? It's electric. That's the thing. The greenhouse gas emissions off of that are going to be so much less, not because you're burning coal instead of gasoline, but because you don't have an internal combustion engine. And so when my car breaks down, like 12 years from now, because I got a Honda, like, I'll probably get an electric car. And they'll be better by then. But even there are some electric cars that have like a gas-powered engine, but it's not internal combustion like we think of it. And then if they have to run off of gasoline, they can get like 8 miles a gallon, because the way we make engines is really stupid. So y'all be engineers when you grow up and come up with a better engine for cars, okay? But this is really a lot of our, we wouldn't have to change our quality of life or standard of living if we would just change our car engines. But like the people that lobby for the car companies really wouldn't like that. So all of us have to suffer because of that political interest there. Agriculture, we could reduce methane. Remember that methane? I was trying to tell you about that. And the rest, reduce, reuse, recycle, all that stuff is going to reduce energy input. Cap and trade, the Kyoto Protocol, right? So we didn't sign, we signed the Kyoto Protocol. We did not ratify the Kyoto Protocol. So remember, Montreal is cold, and so CFCs are refrigerants. The Kyoto Protocol, this is climate change, Kyoto, kind of all starts with a C sound. And so we were the only industrialist nation not to ratify this, which means that we didn't come back to our country and do something about it. So we're still not there. And so we are like after China, we make the most carbon emissions. And the only reason China makes so much carbon emissions is because they're making our crap for us, okay? And so other industrialized countries are not, thank you, United States. They're not really enamored with us right now because of this. They're not digging the fact that we won't get on board. We're trying. I mean, like I said, they did get some legislation and try to pass it through a couple days ago, but it just didn't work out. So the United States, like I said, it emits 20% of the world's greenhouse gases, but won't take action. We're one of the leading causes, but we won't take action. So, because the United States lack of action, other little states and municipalities have actually come together and signed this climate protection agreement to meet or beat the Kyoto Protocol. And so, because the federal government won't really do a whole lot, we're trying to do our own thing, or not us, we're not part of this, but other states are trying to do their own thing to try to cut carbon dioxide and other greenhouse gas emissions, which is pretty cool. So here's what a cap and trade looks like. You establish a limit on emissions, and then once you establish that limit, if a power plant or a factory in this case goes below that, they have extra allowances that they can sell to this factory that's going above the limit, and they can get money. So it's a reward system. So I like this for carbon dioxide. I feel like that wouldn't raise the cost as much. It's just forcing it. I would like a reward system better. So Chicago's doing some stuff, like I said. The European Union has a great cap and trade system on carbon dioxide. It started out to be a little bit high, like the limit was a little high, but then they're like gradually bringing it down, which didn't like increase prices of electricity right then for them, which was nice. Carbon tax and carbon offset. These are just ways to offset your carbon emissions. So carbon footprint, this is like your ecological footprint except for the amount of carbon you put out. And we made it. I do want to give you guys some time to talk with your partners about the project. So if y'all don't mind, I just want to go through I'll just go through this. I'll make it a little bit faster. Is that okay? All right. So global warming is defined as an increase in Earth's average temperature, so C. Which of the following greenhouse gases is of major concern or most concern? That's A. And the reason it's A is because B and C, as far as CFCs and methane, they're more powerful as a greenhouse gas, but like their concentrations aren't as high. And then water vapor is good and it's there, and we didn't do that. So what is a proxy? It's all of the above. A proxies on the second question there. Which of the following combinations are both major contributors to global warming? The two most powerful contributors are fossil fuels and deforestation, so B. Which statement regarding climate change is true? B, there is a broad, clear scientific consensus that climate change is a pressing issue. It's pretty funny. Read letter D. The book authors were being very sarcastic. Because, like, some people in the private sector have said that scientists have changed data for personal gain. No. They want a personal gain. They've been a scientist they've been a petroleum geologist or something. So climate change causes which of these? So of course it's always D, right? That's not a real thing on real tests, but for whatever reason these PowerPoints like that. Kyoto Protocol was written. Gas emissions since then in the United States have actually increased because we have no reason to cut them. Cap and trade, that is where industries are going to buy permits for their emissions. So C. And then the last one, which area is going to have increased droughts? That's the brown areas. So you can tell that North Africa is going to have increased droughts. All right, so go ahead and get with your partner. And what I'm going to do is I'm going to call y'all up one group at a time and give you your directions as far as your content that you have to cover.